Questions? I'm going to start by talking about renormalization in the only way that makes sense to me, which is, I think, equivalent, of course, to all the other ways of doing renormalization. But what bothers me is that all the ways that I've seen in books have explicit cutoff parameters and then coupling constants that are small, that are said to be the renormalized coupling constants, and then bare coupling constants that are zero or divergent. In other words, the thing doesn't make any mathematical sense, as far as I can see. So I'm going to take a different tack here, and the idea, the basic principle is one of humility. That is to say, we don't know what's going on at short distances, so we really can't compute anything. What we can do, though, is use our theory to compute how something would be at one energy if we measure it at another energy. So we can predict how it changes with energy. Not what it is in any particular energy, but how it changes with energy. And presumably with other parameters of the theory. To illustrate this in a simple context, I want to go back to the phi cube theory and go to Schwarz's equation 16.7. And what I'm going to do, well, I'll write down his 16.7 if I can find it here. He has I and loop of P is G squared over 2 integral d4 k 2 pi to the 4th integral 0 to 1 dx 1 over k minus p 1 minus x squared plus p squared x 1 minus x minus m squared plus I epsilon squared. Now the problem with this is that this is a divergent integral, so this is the thing that we can't calculate. Notice, by the way, that k and p are 4 vectors. This is actually a linear combination of 4 vectors squared in a Lorentz invariant way, with, of course, Husserl's measure. So what I'm saying is, don't compute this. Instead, compute the derivative of this with respect to p squared. And that is and the derivative with respect to p squared is p mu over 2p squared d by dp mu of I ml of p. So, in other words, compute this. Well, what is this? This is p mu over 2p squared. Well, of course, it's just the derivative of this. So it's d by dp mu g squared over 2 integral d4th k 2 pi to the 4th integral 0 to 1 dx, and then 1 over this quantity here, which I'll just write as curly bracket squared. So that's the derivative. That's what we have to do. Now, when you differentiate with respect to p mu, that's going to pull down another factor of this. It's going to make this thing cubed. that will be 1 over k to the 6th in the denominator. We'll have a convergent integral. So what we get is p mu over 2p squared, g squared over 2, integral d fourth k, 2 pi to the 4, integral 0 to 1 dx. And now, differentiating this, we get minus 2. And now the derivative with respect to p upper mu of this thing, and this part is the one that's easier to do. That's 2 lowercase p mu times x, 1 minus x. And then the derivative of this thing is a 2 from that, and what's left is k mu minus p mu 1 minus x. So it's that, and what do we have in the denominator? We have the same old denominator but now cubed. So in other words, by computing the derivative of this thing, we have something that's finite. And now that it's finite, because there are 6 powers of k, only 1 in the numerator, and the k mu integration would vanish, wouldn't it? Because, let me see,
Are you missing a 1 minus x?
Yeah, we have to, what about?
Are you missing a 1 minus x in the numerator from from your k minus p 1 minus x squared?
Oh, it's, no, I think it's this. We're differentiating this thing. So this is
differentiating what's inside of it.
yeah, but it's basically it's like differentiating k squared.
Okay.
Actually, it's wait a minute. It's simpler than that. Yeah, maybe I did this, but let's do this more carefully. What we've got is k mu minus p mu 1 minus x times, or let us say k nu. K nu minus p nu 1 minus x. And now, yeah, you're right. You're right.
Okay.
If we differentiate this, we get the we actually get 2 terms, don't we? We get, all right, we get, if we just, all right, there's the 2. We're differentiating with respect to this upper mu, and so we get a minus 1 minus x, and then this term. So what I'm missing here then is 1 minus x and a minus.
Yeah, in between the 1 minus x's.
Is that right?
You're just missing one parenthesis in between the 2 1 minus x's, but yeah, I think so.
Oh, you're right. Okay. All right, so this is what we have, and what I'm a little bit bothered by is that I wanted to get, well, the fact is that the k mu integration, see, I'm worried now that I hadn't noticed this, that I thought that once I had k to the sixth here, everything would be just fine. But in fact, k over k to the sixth is 1 over k, and that does have a log divergence. But I think it's okay because I think this term will go away. So what we do is we shift. Let's assume that this is suitably convergent, okay? So we can do the shift. So we let k mu. Oh, actually, you get 2. Pointing out a mistake. Nothing better than that. So we now let k mu go to k mu plus p mu 1 minus x, and that cancels this term. And so what we have then in the numerator, pulling out the factor of 2, the factors of 2, and this is effectively, this thing here is the same thing as d dp squared of I and L. So this is a way of writing d dp squared. And so what I'm getting then is d dp squared of I and L of, let us say p squared, because it really is p squared, is minus p mu over p squared g squared integral d4 k over 2 pi to the 4th integral 0 to 1. And now the denominator turns out to be k squared minus m squared minus p squared x 1 minus x, well, plus I epsilon, and now it's cubed. And up in the numerator, what we have, after pulling out the after shifting with k mu and pulling out the 2, is we have p mu x 1 minus x, and then minus k mu times 1 minus x. Now there's just k squared down here. And so this term goes away because it's odd. We're integrating over all k, and so you have plus k minus k. So this term is all 0 then. And we just have that. And now p mu is p squared, and so altogether this is just g squared, integral d4 k over 2 pi to the 4th. And what's left then is 0 to 1. Again, if I haven't made a mistake somewhere, what I have left, at least when I did the calculation this afternoon, is this divided by, again, k squared minus m squared minus p squared x 1 minus x. Although, why don't we just make this a little bit simpler? Minus m squared plus I epsilon cubed. So that's our integral. Now that's perfectly finite. And so what I'm suggesting is that we may be able to do renormalization theory without any infinities at all, without keeping this just to be the ordinary coupling constant, some small number, and we just compute the derivative. And so what we say is that, well, in fact, we can go a little bit further. If we call this quantity here, in fact, all right, let me put back the parentheses. If we call this whole thing delta, which was Schwarz's notation, then this integral is actually convergent. And I'll say something later, in a few minutes actually, how to do such integrals. But, you know, of course, these days we're kind of cavalier about these things. We can just say, well, I don't know how to do it, but mathematics does. Just have mathematics do it. Which is what I did this afternoon for the x integral, actually. I'll show you how to do this sort of an integral. So this thing then turns out to be g squared with a minus I over 32 pi squared 1 over delta. That's just the d4th k integration. We then have an integral 0 to 1 dx x 1 minus x. And, right. And so, somehow I just see that there's I just made a switch from minus I to plus I here in my notes. And there's an overall minus sign here. So when you see this formula here was just for the d4th k integration. We have an overall minus sign that came from here, right? And somehow I didn't bring that down. So there's a minus sign there. And then when we do the d4th k integration, there's another minus sign. So now we're with a plus sign. And so this thing, in other words, is I g squared over 32 pi squared integral 0 to 1 dx x 1 minus x over m squared minus p squared x 1 minus x. Okay. Now you remember that Schwarz says, well, we're really going to be looking at this for p squared negative. And there's a good reason for that, because if p squared is positive and m squared is positive, then there's the possibility that as you integrate x from 0 to 1, you can get a pole here. And that, I think, is the origin of what's called the large logarithm problem. And that is not something related to ultraviolet renormalization. So let's forget about that and what Schwarz did, namely by saying we're really talking about negative values of p squared, because we're going to be interested in corrections to, in other words, we're going to be looking at this diagram where p squared is negative. And now I said to myself, well, duh, I can't do that, but mathematically can. And so I said, assuming m positive, and I call this, let's call this plus q squared. So q squared is minus p squared. And so assuming m positive and q positive, integrate this from 0 to 1. And Mathematica said, aha, I g squared over 32 pi squared. And now what we have is q minus 4m squared arc tan hyperbolic Q, and I did not write this with enough parentheses to know whether it's like this or whether the arctan is divided by the square root. And it's on a computer screen in my office, but I did not write it clearly enough. So that's it is inside this. The next line I wrote it more clearly, so it actually is like this. And so what does this tell us? This tells us then that m loop at q squared is m loop at some q0 squared, and this thing we have to measure because we can't compute it, because we really can't compute anything because we don't know what's happening at really short distances. But we can measure that, and then we can compute what this is. Then if we measure this, we can say the theory is true or not. Okay. And so the idea is that it's that plus g squared over 32 pi squared integral q0 squared to q squared of, well, actually 1 minus 4 m squared over q arctan hyperbolic q over the square root of 4m squared plus q squared. All that in square brackets dq squared over q squared. Okay. That's a finite integral, and in fact it's an easy integral in the limit Schwartz takes, which is m equals 0. So let us set m equals 0, and then we get that ml of q squared is ml of q0 squared plus g squared over 32 pi squared integral q0 squared to q squared dq squared over q squared. And so that's ml of q0 squared plus g squared over 32 pi squared log q squared over q0 squared. So here we get the same result as in the book, but we haven't had to deal with any infinities at all. And so I think this is a better way of doing renormalization. Now the question is, can you do this for all renormalization theory? Well, I don't know. I'm not a specialist in renormalization theory. But I think what I'll try to do as we go through the rest of renormalization theory following Schwartz, I'll try to give you this version of things. And I think it actually is pretty easy to do that. But let me now switch to, and I sort of like this because it reminds me a little bit of what, the basic idea of quantum mechanics. You can't measure, it's a limitation on measurement. Well, here this is a little bit, this is also a limitation on measurement. We can't measure things at arbitrarily short distances, so we don't know what's going on. And so we can just say, well, we'll measure this and then compute that. And then the fact that G is just always a small parameter, rather than screwing around with this, with having two G's, one infinite or 0 and the other one finite, it seems to me that was not very, very good. So let me just remind you of some of these Feynman things. One is the result 1 over AB. I derived this for you last time, I think, or the time before that. It's integral dx 1 over a plus b minus a x squared. And another way of writing that is integral 0 to 1 dx dy and delta of x plus y minus 1. And so here y is 1 minus x, so y also is somewhere between 0 and 1. So in a sense, it's also integral 0 to 1 dy if you want. It's that times 1 over xa plus yb squared. So that's one way of writing it. And then other identities due to Feynman are 1 over a bn is integral 0 to 1 dx 0 to 1 dy delta x plus y minus 1, and now n y to the n minus 1 over xa plus yb to the n plus 1. And I suppose you can actually derive this from that by just differentiating with respect to capital B, I would think. Isn't that right? So that's one way of doing it. And another Feynman integral is 1 over ABC is 0 to 1, let me just say dx, dy, dz, they're all 0 to 1. Delta x plus y plus z minus 1, and then 2 over xa plus yb plus zc cubed. So those are very, very symmetrical integrals, and we've seen how we can use them. In fact, that's of course what I did here, but I didn't do it explicitly because we had already done it in a previous class. Okay, let me get a sip of tea. Any questions? By the way, you can always interrupt for questions, and you don't have to wait for me to invite your question. Okay. Now there are these things called Schwinger parameters. And for example, these are just integrals. I over A is the integral 0 to infinity ds e to the I sa. And so that's an elementary integration. Of course, what you need here is imaginary part of A should be greater than 0. I mean, it certainly holds when imaginary part of A is greater than 0. If A is real, it might work. I'm not sure. It's also true that I over A squared is an integral 0 to infinity s ds e to the I sa. And another one is 1 over AB is minus 0 to infinity ds 0 to infinity dt e to the I sa plus itb. And one can actually derive Feynman's identity from that. And another one that I guess, just on the fly, I don't quite see the derivation of this, but 1 over a to the n b to the m is gamma of n plus m over gamma of n, gamma of m integral 0 to infinity ds s to the m minus 1 over a plus bs to the n plus n. And for the case nm equals 1, you have 1 over ab is integral 0 to infinity ds 1 over a plus bs squared. Okay. So these are some Schwinger identities. Let me remind you of the definition of the gamma function. Of course, you can Google it the way you can Google anything, but damn it, I wrote it down here somewhere. Great. All right, here we go. Gamma of z is integral 0 to 1 e to the minus t. Wait a minute, it's not 0 to 1, it's 0 to infinity.
0 to infinity.
0 to infinity, e to the minus t, t to the z minus 1 dt. Oh, I wrote it the wrong way. And so if you set z equal to 1, you see the thing simplifies, and you just have integral 0 to infinity e to the minus t dt, and so you get gamma of 1 is equal to 1. And gamma of z itself is a definition of z minus 1 factorial, so that extends factorial to arbitrary z. But you can see here that if z is 0, then you've got something that converges at large T, but has a pole at small t. And so the thing actually diverges there. And in fact, gamma of small z, let us call it epsilon, is 1 over epsilon minus this constant, which is called gamma sub e, which is the Euler-Mascheroni constant, plus something for epsilon plus dot, dot, dot. So in other words, it's clearly an infinite series. This gamma sub e is about 0.577, and of course, an infinite series there. Okay, any questions? The gamma function, by the way, I discussed the gamma function in chapter 4 of my book, and also probably in chapter 5. There are all kinds of amazing identities involving the gamma function. And the reason for that probably is that it involves just a power of t and then an exponential. And exponentials are functions that are well suited to identities. Of the various identities, one is sine, sine of pi x is pi 1 minus x over gamma of x, gamma of 2 minus x. Cosine pi x is 1 minus 2x over 2x, gamma of 1 minus x, gamma of 1 plus x, over gamma of 2 minus 2x, gamma of 2x. So these are things in Appendix B, which I'm describing here. There's also a beta function, beta of AB, and this is by definition gamma of A, gamma of B over gamma of A plus B. And you can see that hiding here because this is A and that's, no, sorry, it's not hiding there. I thought it was hiding there. No, it's not hiding there. Anyway, this beta function, it turns out, is integral 0 to 1 dx, 1 minus x to the a minus 1, x to the b minus 1. So that is an important formula, and in fact, I think that allows one to do the following integration. dk k to the a over k squared plus delta to the b, and this is just length of k here. This is delta to the a plus 1 over 2 minus b, and then gamma of a plus 1 over 2 gamma b minus a plus 1 over 2 gamma of b. And this integral, of course, is 0 to infinity. And if you now combine this last expression together with the formula for the formula that I derived last time, or the time before that, remember the surface area of a sphere in d dimensions, which is really the d minus 1 sphere. But anyway, this thing is 2 pi to the d over 2 divided by gamma of d over 2. And if we combine those things together, then we can compute, use this, and we use that, and we can compute some of these integrals that occur in dimensional regularization, or for that matter, occur just doing things the way I was doing them there. In particular, the integral d to the d, this is in d dimensions. So the idea, as I said to you, the idea of dimensional regularization is to go to d-dimensional space and to imagine and to use the fact that various integrals that diverge in 4 dimensions converge in 3.9 dimensions, let us say, and probably converge even better in 2.9 dimensions. And so one can do these various integrals. So one of them is k squared minus delta plus I epsilon squared. And it turns out that that is I over 4 pi to the d over 2, 1 over delta to the 2 minus d over 2, gamma to the 4 minus d over 2. One can also do dk over 2 pi to the d, k squared over, so this is the same thing, k squared minus delta plus I epsilon squared. And of course what one is doing a Wick rotation, and you then get minus d over 2 I over 4 pi to d over 2, 1 over delta to 1 minus d over 2, and then gamma to the 2 minus d over 2. Now you can see that this thing diverges if you let d go to 4, because you have gamma of 0, which is 1 over 0. This one, in fact, diverges at other places. Let's see, gamma of minus a half actually is finite, isn't it? I'm a little puzzled then. What is it? Oh no, it's That's gamma of minus 1, because you have minus 2 over 2 minus 1. Gamma minus 1 is also infinite. So the gamma function has poles at 0 and at all the negative integers. And so that's why this thing is 0. Another one, which I actually used this afternoon to do one of these integrals, 2 pi to the d, k squared over, no, it's not this one, it's the one beyond this, plus I epsilon cubed is d over 4 I over 4 pi to the d over 2, 1 over delta 2 minus d over 2 gamma, and then again 4 minus d over 2, so again this has a pole. And now here's the one that I used this afternoon, dk over 2 pi to the d, 1 over k squared minus delta plus I epsilon, now cubed. So this thing in 4 dimensions is d4 over k to the 6th. And this one is minus I over 2, 4 pi to the d over, let me get this straight, 4 pi to the d over 2, yeah, that part was right. And then 1 over delta to the 3 minus d over 2, gamma 6 minus d over 2. Okay, so this one, as you go to d over 4, is minus I. This is d over 2 is just 2. 4 pi squared is 16 pi squared times 2, 32 pi squared. That's that familiar number that has come up about 10 times already. D over 2 is 2, so this is just 1 over delta. And gamma 6 minus 4 is 2, 2 over 2 is 1, gamma of 1 is 1. So it's minus I over 32 pi squared 1 over delta. And this is the formula that I used back here. To do the k integration. In other words, to go from d4 k 2 pi to the 4th, k squared minus delta, I just got I 32 pi squared 1 over delta, and the minus sign, cancel that minus sign. So that's where that came from. Let me get a more chalk. Any questions? Okay. Well, a little more stuff about dimensional regularization here. You remember that I said that how to figure out dimensions in dimensions of fields in 4 dimensions. So suppose we have something like L for QED minus a quarter P mu A nu minus P nu A nu. I'll write squared, but which is what Schwartz wrote, but you know you have to get the correct Lorentz contraction. I gamma mu d mu minus m psi, and then the rest of the covariant derivative is minus e psi bar gamma mu psi a mu. Okay. Now, the normal case is when you have 4 dimensions, and then so you have integral d4 of x times L, and you want the units of this to be 1. That is to say, you want it to be dimensional. So this is the action. And so let's just do these things simply. One of the simplest ones is this is L to the 4th. So we have L to the 4th Here we're talking natural units as opposed to unnatural units. L to the fourth psi bar psi m is 1. Well, m is units of energy. M cancels 1L, so L cubed psi bar psi is 1. So the units of psi bar psi in 4 dimensions are mass cubed. But now if we're in d dimensions, it's different, because instead of having L to the fourth, we have L to the d. And I'm going to leave m, so now we would have L to the d minus 1 psi bar psi is 1, right? So that means that the dimension of psi bar psi is, let us say, mass to the d minus 1. So setting d equal to 4, we get mass cubed, which is fine, but we get this peculiar dimension if it's mass, if we're in 4 dimensions. Anyway, let's look at A. So A looks like this. So then we have L to the d. We have the square of a derivative, so that's L squared. And then we have A squared. So all that has to be 1. So that means L to the d minus 2 A squared is 1. So A squared has to have dimensions mass to the d minus 2. What else? Let's look at this thing here. We've said, let's suppose psi bar psi has dimension m to the d minus 1. Because what I did was I kept m having dimension of mass. And okay, so the dimensions of A is m to the d minus 2 over 2. The dimension of psi, taking the square root of that, psi has dimensions m to then d minus 1 over 2. And m has dimension of m. Okay, so I followed the same convention as Schwartz. Now what about E? Well, we've got the dimension here is L to the fourth E, psi bar psi is m cubed, A is m to the d minus 2 over 2. And so all of this has to be 1. So this is LE m to the d minus 2 over 2 equals 1. This is m to the d over 2 minus 1. That's not going to work because L is 1 over m. So this is really E to the m d over 2 minus 1. Dimensions of L are m to the minus 1, so this is minus 2 equals 1. So the dimensions of E are m to the 2 minus d over 2. So that means that that E, which always was dimensionless, in d dimensions acquires a dimension, a funny dimension. And what people do is they say, we want to keep E dimensionless. And so we're going to say, we're going to basically replace E by saying that E goes to E times some parameter, mass parameter mu to the 4 minus d over 2. So 4 minus d over 2 is the same thing as 2 minus d over 2. And mu is then just an arbitrary parameter where mu is just a mass. And this mu is not thought to be 0 or infinity or anything else. It's just something that's stuck in order to keep E dimensionless. You could let E be this, and everything would be all right. And in fact, I think much of this dimensional regularization stuff really simplifies if you do things the way I suggested at the very beginning of the lecture. And in fact, I hope to get back to that in the next 15 minutes or so. So let me just say a little bit about what is happening here. For example, we have in dimensional regularization, we have d fourth k over 2 pi to the 4th. Let us say e squared over k squared minus delta plus I epsilon squared. Now this has a logarithmic divergence. Let me just take a sip of well, what does this go to? Well, we're replacing e squared by e squared mu to the 4 minus d. So this is going to be then mu to the 4 minus d integral dd of k over 2 pi to the d e squared dimensionless over k squared minus delta plus I epsilon squared. And then that then, by using one of those integral formulas, that then is mu to the 4 minus d I e squared over 4 pi to the d over 2 gamma to the 4 minus d over 2 1 over delta to the 2 minus d over 2. So this is what happens when you do the integral in d-dimensional space using the formula for the d-dimensional, the area of a sphere in d dimensions. And so then the next thing is to expand this around d equals 4 minus epsilon. And so this thing then becomes I e squared over 16 pi squared. So we've got a big change now from 32 to 16. 2 over epsilon plus, and then minus this Euler-Mascheroni constant, which is 0.577 or so, log 4 pi plus log mu squared minus log delta plus order epsilon. And so one can combine that into I e squared over 16 pi squared 2 over epsilon plus log of 4 pi e to the minus gamma e mu squared over delta plus order epsilon and so forth. And so it turns out that this combination occurs a lot. So now one defines mu tilde squared to be 4 pi e to the minus gamma e mu squared. So you can see we're getting is getting very technical. This is just a convention, okay? These guys, in other words, the people who do renormalization for a living, don't want to write things like this all the time, so they introduce an abbreviation. So at that point, this thing turns out to be IE squared over 16 pi squared 2 over epsilon plus log n tilde squared over delta plus order epsilon. All right, so that was that integral that was divergent. Let me maybe stop now with that and switch back to what I was talking about earlier, back to the physics, and let me skip to the spinor QED case. Okay, so for spinor QED, what we have is a photon coming along, K, and if we have this one going like that, then that one is K minus B, like that. Okay. This thing turns out to be minus IE squared integral d4 K 2 pi to the 4th I over P minus K squared minus M squared I over K squared minus M squared. And then, this is the easy part. The hard part is times in the numerator trace of gamma mu K slash minus P slash plus M gamma nu K slash plus M. There's an overall minus sign here. Minus signs come out if you have a fermion loop in the calculator. You get an extra minus sign. And that comes out from expanding. In other words, what we really have is e to the integral IL d4 x, some field operators here, or some creation operators here, some annihilation operators there. Then we expand this thing, and if you just keep track, you'll see you get a minus sign. The trace is 4 times minus P mu K mu minus K mu P nu plus 2 K mu K nu plus G mu nu minus K squared plus P dot K plus M squared. By the way, I should have mentioned that the fact that this is only logarithmically divergent is an improvement over what we would get in phi cubed theory. If we had a phi cubed, well, in phi cubed theory, if we have a loop like this, it's quadratically divergent. This one is only logarithmically divergent. So then, if we do the d by d p squared trick, we're going to have something convergent without my even having to wave my hands at something that we can shift anyway, and then we get the thing being odd. In any event, Schwartz focuses then on the parts that matter, and the parts that matter are the parts that don't have a p mu. So we can forget about this term and this term, because when you couple them to conserve currents, they vanish. And I think this guy is going to go also. No, he keeps that one. Okay. So this thing here is called pi 2 mu nu, and it's minus 4 e squared integral d4 k over 2 pi to the 4th, and 2 k mu plus g mu nu. Let me just write ditto over then the denominators are p minus k squared minus m squared plus I epsilon, k squared minus m squared plus I epsilon. Okay, so those are the things. You then use a Feynman trick, and you have an x integral, and if we cancel the I there, then we get that pi mu nu 2 is, all right, we have a little bit of time, so I'll write this down in 2 steps. 4i e squared p fourth k 2 pi to the fourth 0 to 1 dx. And he's already done the shift. What I would say is, that is to say, a nicer way of doing it, I think, is at this point to do this business of d by dp mu over 2p squared. In other words, apply this operation, which is effectively d by dp squared, to this thing, and that would then just act on the p here, and it would give us something that was higher. It would give us this thing squared, and then we would use one of those Feynman things, 1 over ab squared, and then we'd get an integral that was entirely convergent. Then we could shift, because it's convergent. Okay. What Schwartz does is he has this thing that is, it's the same numerator, so I'll just write, well, it's not quite the same numerator because he has, he shifts. So he shifts, it's the same shift, and let us just say it's 2k mu k nu plus dot 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 over, and what's down here is k squared plus p squared x 1 minus x minus m squared squared. By the way, when I said you'd have a quadratic divergence here, the reason you go from quadratic to logarithmic is that this thing has electrons and positrons, and so that has improved the, has removed some of the singularities. So you have then this expression after shifting, and now you can write this in dimensional regularization form. And I'm going to go back to the back blackboard to do the rest of this because there's some blank space here. What you do, what you get after you do this is that this integral, which is logarithmically divergent, you write it, maybe we have time for actually to write the whole thing, so you have pi 2 mu nu is you effectively get minus 8 p squared g mu nu e squared over 4 pi d over 2 gamma to the 2 minus d over 2. And of course, gamma to the 2 minus 2 is 0. And you let d go to 4, so that's a divergence. Mu to the 4 minus being 0 to 1, x, 1 minus x. And then you have 1 over the m squared minus p squared x, 1 minus x. All that to the 2 minus d over 2. And so this turns out to be minus e squared over 2 pi squared p squared g mu nu integral 0 to 1 dx x 1 minus x. And then 2 over epsilon, this epsilon is the 4 minus d thing. Or d, 4 minus d, I think is epsilon. Plus log of the mu tilde squared over m squared minus p squared x 1 minus x plus order epsilon. You're letting epsilon go to 0, so we can forget these guys. Okay, so that's the expression. But now, so suppose we take advantage of all of this arithmetic and calculus and now apply the technique of ddp squared. Well, there's p squared here, p squared there, no p squared here. Oh wait, there's a p squared. There is a p. Oh, yes, sir. I hadn't noticed that now. E by dp squared here. I thought this would be 0. All right, let me see. Is this integral perhaps 0? No, 1 minus x is positive and x is positive, so that's certainly not 0. Well, nuts. I thought this would be. Of course, you know, we could have. All right, so maybe the best thing is not to go to use all the dimensional regularization, but instead, in other words, to go back to this expression. So, in other words, we go back here and say this is our pi. Our pi, and what we're going to do is we're just going to calculate the derivative with respect to p squared, which is the trick is d by dp mu, p mu over 2p squared. Apply that to this. That will make this a squared term, and it'll bring up, at worst, a linear power in k. But we will then have k to the 6th, and actually, I now see I have a 2 k's here, which I hadn't noticed before. Well, I'm going to have to look at this more carefully. Anyway, I think it's better, but I'm not able to carry that thing out because, see, what I thought was that the only problem was the 2 over epsilon. That doesn't depend upon p. You differentiate, it goes away. And in fact, that doesn't seem to be, that trick doesn't work. But I think nonetheless that, you see, this thing really isn't quite, it looks as though it might be quadratically divergent, but it really isn't. It's really logarithmically divergent. And so when you do the differentiation, I think you get something convergent. And then what you have is that pi 2 at p squared would be some integral of something finite plus pi 2 at some p0 squared, and that's the thing you measure. And the theory then gives you how it varies with p squared. So I'll have to look at that more carefully to dust it off. How about questions over there? Any,
Sure.
Yeah.
So when you have a p mu over 2p squared there, in your circle over your left shoulder.
P mu over 2p squared.
Yeah, so we multiply the p squared, doesn't it just cancel out over there?
Oh, God bless you. I think you're right. Two more candies. All right, let's just see that. Well, that, I don't know. I mean, this funny expression is just d by dp squared.
Right.
So d by dp squared, you know, you get something non-zero here.
Okay.
And then you leave that, still have the 2 over epsilon. So, nice try.
On back.
No, you can have it. Anyway, it seems to me that by being suitably clever and differentiating enough times, one can always, I think one can reformulate renormalization theory so that there are no infinities and everything is just termed by measured quantities and by the theory, and and then one can also then apply the idea of the running coupling constant, which is that you say that the tree level diagram with a running coupling constant is equal to the actual value, and that thing is the value measured plus some integral. And so you get a running coupling constant. We find out how the coupling constant runs. We'll get to that later. All right, I guess we should quit now.